That's just a summary of what we did at the end of last time. You should all have that written down. Either it's written down in your notes, or it's written down in my notes, which are available online. So I just needed it to be up on the board so we could talk about it again. So this is the definition of a manifold. And there's some words missing, such as is a topological space such that, so on. But this is just a reminder because we're going to prove that something is a rational algebraic variety. So we're going to have to verify these things in order to list what we need to verify. I figured we'd put it back on the board. But just as a matter of an example, or first as a matter of what is it supposed to mean. So what it's supposed to mean is you have some space, right? You can think of the space as being like the surface of the Earth or something like that. Yeah, and you want to know that what kind of space is the surface of the Earth? Well, it's kind of a nice looking space. Right? When you stand on a point on the surface of the Earth, then around you, an open set around you, looks like a piece of the plane. Now, the whole surface of the Earth is not a plane, right? But it's sort of locally, it looks like a plane. So the idea is you'd like to say a manifold is a space that locally looks like an open subset of a vector space. That's what we'd like to say a manifold is. And this is just making that precise. So if you're standing on the surface of the Earth, then in what sense does it locally look like the surface of in what sense does it locally look like an open subset of the plane? Well, in the sense that, if you give me the surface of the Earth, then if you're looking at your Google Earth and you zoom in pretty far, then what you see is a planar piece of your screen. Right? And that would be a chart for that particular little piece of the surface of the Earth. Right? And then you sort of move your screen a little bit, you move your view, so now you're looking at a chart for another piece of the surface of the Earth. And so you have all these charts, and these charts cover the entire surface of the Earth, right? So that's what this says. It says that your chart, you want a map of the entire surface of the Earth, but you don't want the map entirely all at once. You want it in little pieces, and you want each little piece to be a little planar bit, right? You want each little piece of the surface of the Earth, of your map, to be a little planar bit. So each U alpha is open in some affine space of dimension D. For the surface of the Earth, it's dimension 2, and F is the real numbers. So we're just saying that you can cover the entire globe by looking at maps of little pieces, and the little pieces you can put on the screen. And although the little pieces aren't actually rectangular, they're very slightly curved. They're close enough to rectangular that you can think of them as being rectangular. And then the map that goes from that little rectangular piece into your space X, it hits a subset called X alpha. And I want this to be a homeomorphism. Like you're not breaking things. You're not introducing a hole from U alpha to go to X alpha. You're taking a little piece of a rectangle and you're continuously putting on top of the part of the surface of the Earth that it's supposed to represent. And what does this say? This says that if Feng is looking at a map of a certain piece of the surface of the Earth, and Nicole is looking at another map, but their maps overlap on parts, then we want to say that the directions that Feng is going to give are the same as the directions that Nicole is going to give. That's what this thing says. This says that if you take the part that Feng is looking at, and then you sort of map it to the surface of the Earth, and then you go back to where Nicole is looking. That's what this says. So you go from U alpha, you go into X, and then you go back according to Nicole's map pi beta. Then what you get is supposed to be, well, continuous, or a ratio of polynomials, or anything in between. And that tells you that you have a space that's of the appropriate type. Yeah, so for example, if you have just a circle, right, then that's going to be, let's just say it's going to be maybe this fit. And remember, we needed that U alpha is open inside of an affine space of dimension here D equals 1. Right? And there are two charts. It's going to be this thing, union, let's say, this thing, right? So you've got, I suppose I should draw them in blue and red like I did last time. You've got this bit, like this, and you've got this bit like this, right? So it's going to be the blue one union the red one, like this, right? So this is going to be, there's a map that goes like that, from an interval, an open interval to that. There's the map that goes from an open interval here to that one. What would be the intersection of these two? What would U alpha, what would X alpha beta be here? Right, so X alpha beta is the union of these two yellow guys, and that's going to be this bit over here and this bit over here, as well as this bit over here and this bit over there. And the point is that this is the map that goes from, okay, now what is the map that does this? How do you take this one? So this is U alpha beta, so this is, this I suppose is U alpha beta here, and this is U beta alpha. What's the map that goes from U alpha beta to U beta alpha in terms of these little tiny intervals? What does it do? You have to
it's a composition of pi alpha and pi inverse beta.
Sure. Yeah. So you go up to here, then you go over to here, and then you go back down. But what does it do to these little yellow things? In the end, what is the actual map? Just describe it geometrically in terms of these little intervals. This little interval goes where?
The little interval on the left.
Yeah. So this one goes up to here, which is the same as this, and then it goes down to there. And what can you tell me about the? Does it reverse orientation, keep the orientation? What does it do? Right, so this point, let's call this point 1, and that's 2. Have I done things in a way that makes it so that, yeah, so then what's this? That's 2 and that's 1, right? So the map, it flips this interval to get to that one. And how about this? This is 3 and 4. Right, so this is going to be the point. Let's see now if we do this right. So 1 and 2, so that's 1. That's 1. That's 2. And then you've got 4 and 3. Is that right? Yeah, so what is it over here? This is down here, that's, so this one is 3, and that's 4. We agreed? Yeah, so the map, what it does, it sort of flips these intervals. Yeah, but still, it's still a homeomorphism. It's just that, so now what's happening is that Feng is reading his map, and then Nicole, for whatever reason, is looking at hers in a mirror. Okay. Questions about the definition of a manifold? The reason to have these conditions down here to make it continuous, or down to ratio of polynomials, is that if you want to know what is a polynomial function on something, if you've got a manifold and you say, you've got the sphere, let's say, and you want to know what's a polynomial function on the sphere, the answer is, I don't know what a polynomial on a sphere is. But I do know what a polynomial on an open subset of a vector space is. Right? So let's suppose that I have a function on the sphere and I want to know that it's a polynomial. I say, oh, well, is it a polynomial on this chart? And the answer might be yes. But then I have to ask the question, if it's a polynomial on this chart, what if I looked at a different chart? Is it polynomial there? Well, if I know that these transition functions, these are called transition functions. If I know that these transition functions are ratios of polynomials, then if I had a polynomial, or let's say a rational function on this open subset, if I have a function on the sphere and I ask, is it rational? Then if it's rational on this open set, then it's going to be rational on every other open set, at least where they overlap. And that's the point of having ratios of polynomials be the transition functions. It says that the notion of the kind of function that you get is independent of which chart you chose. Yeah, go.
I actually do have a question about the definition of a manifold. So when you say something's a topological space, does that just mean there's a notion of openness?
Yes, yes, that's right. I've told you that there's A topological space is a space, it's a set that also has a collection of subsets called open subsets. That's literally all it means. And remember, the axioms for open subsets were pretty simple, right? You want any union of open sets to be open, any finite intersection of open sets to be open, and you want the whole space in the empty set to be open. And really, that's it.
Is it the same affine space for all alpha?
It's the same D.
It doesn't have to be the same.
It doesn't have to be the same affine space, but it has to be the same D. Right? I have to be able to know what is a polynomial function on it. And if I have any affine space of dimension D, then I know what it means to be a polynomial, or yeah, to be a polynomial function on it. So it can be different affine spaces as long as they all have the same dimension. And then I'd call this a manifold of dimension D. Right? So this D is the dimension. That's called the dimension of X. Right? So this circle, what's the dimension? This is it's a circle. The circle, so we say S1 has dimension 1. Fair enough? Okay. So now we had a theorem that we were going to prove, and I told you that the proof came down to something that's really quite elementary from 221, but we just have to go through and see about all these conditions. So let's take that theorem again. And it says that the grassmannian of k-planes in n space, I say this fancy word grassmannian, but you can just replace it with the word set. The set of k-planes in n space is a rational algebraic variety of dimension k times n minus k with an atlas that we've already seen. With the atlas, and let's say it's going to be pi sigma, and that's going to map f, I'll remind you what these things are in a second, f to the k by n sub sigma mapping to the grassmannian, such that sigma is a k-element subset of 1 through n. Okay? That was the chart, that was the atlas that we wrote down last time. Now let me just remind you what this thing is. So let's see now, f k by n sigma. Anyone remember what this was? Make sure I get the definition right. And then I wrote down, really, I know what I know what I want. I just want to make sure that I wrote down the correct symbol for the thing that I want. F sigma, where did I define it? There it is. Yes, good. So this is the, so it has the identity block ik in the columns from sigma. Yeah? So we're looking at matrices that look like this. And that's k, that's n, and then sigma tells you to look at some, right? So sigma is that subset of 1 through n. And in those things, what you've got is an identity block that looks like this. Now in these columns, so there's intervening stuff elsewhere, but in those columns, it's an identity block. Yeah, so remember that this is an affine. This is an affine space of dimension. Well, you've removed k columns, so what's left is to freely choose the other k times n minus k entries. So this has dimension k times n minus k. Okay, so let's go formally into the proof. So we proved a proposition last time. So we have a bunch of dots here. So the proposition we proved last time implied that x is the union over the alpha of the x alpha. So I'm just going through these conditions that we need to prove. What did that say? What that said was that it actually said that the grassmannian of k-planes in n space. What is that? It's the union over all, whoops, it says S there. I don't know why it says S. It should be sigma in n choose k of g k sigma. Now I need to fix this thing. S should be a sigma. Yeah, it just says, remember what statement this was, right? This looks like sort of a highfalutin, complicated statement. All it says is a subspace of dimension k inside of an n-dimensional space is spanned by k rows. And those k rows have to be linearly independent. So some k element subset of the columns has rank k. Right? If you give me a k by n matrix and you say that, oh, well, these things span as the rows span a subspace of dimension k, then k of the columns are linearly independent. That's all it said. Right? And then I can multiply it by the inverse of those columns on the left and force that submatrix to be an identity matrix. That's all this is saying. Now, I realize that from a point of view of map 221, we just did a lot of complicated things. We just used the fact that rank is well defined. We used the fact that row rank is equal to column rank. We used the fact that multiplication on the left by a k by k matrix takes a linear combination of the rows, but doesn't change the span if the matrix you multiplied with that you multiplied by was invertible. Right? We used a whole bunch of things from linear algebra map 221, but I assume that all those things are known and that you're comfortable with all of them. So this statement it comes down to a bunch of elementary facts from map 221. Again, every k by n matrix of rank k has k linearly independent columns. When you multiply on the left by an invertible, in fact, the inverse of that matrix, you get a matrix that has an identity block there and that has the same row span. I'm not going to write down that proof because that was the proof of the proposition. The point is that we already have the proposition which told us that this was true. But that was just the proof of the proposition that I just reviewed for you. Okay, what else did the proposition prove? The proposition also proved that gk sigma, what is gk sigma? I suppose gk sigma was the image of pi sigma. Is that going to be right? Yes, gk sigma. That's the image of pi sigma. And pi sigma was the map that said, it's the take the span map, right? If you have a map, so if you have a matrix that has an identity block in these columns, then you can take the row span. So pi sigma is take row span. Okay, so gk sigma, that is the matrices that are row spans, sorry, these subspaces that are row spans of matrices with identity blocks in columns from sigma. gk sigma, I'm holding the wrong piece of paper. gk sigma is, remember, homeomorphic to fk by n sigma. And that's, yeah, so that's for homeomorphic to, let's say, f to the d. And that's for d equals n, sorry, k, times n minus k. And that's what we did up here. That's this thing. And so we're going through these conditions over here, right? We've just said that our grassmannian is a union of the images of its charts. We've just said that every chart, the source of every chart, is in fact not just open inside of an affine space, but actually is an entire affine space of dimension d, right? And part of the definition of open is that the entire space is open. So we've just said that the source of every chart, every page, if you like, in our atlas, every chart, it starts from an actual affine space of dimension d. And that affine space is this one. That's an affine space. Right? It's this set, it's the set of matrices that have ones in the appropriate locations in these columns and then anything elsewhere. It is not a vector subspace, but it is an affine space. Not a vector subspace because it doesn't contain zero. These ones prevent you from having zero.
Why is it important that we have an affine space for the definition of a manifold? Or that it's composed of affine spaces?
Yeah, so it's not, we don't need an affine space, we need open subsets of an affine space. And the reason is that a manifold, the intuition is that when you're in a manifold, a neighborhood looks like you're standing in a vector space. A manifold is sort of a globalization of the local notion of vector space. So when you're doing calculus, what you often do is you say, okay, well, I've got my point, I've got my function, and now I'm going to look at an open neighborhood, and I'm going to do all sorts of stuff in that open neighborhood. Well, you could do the same thing for a manifold, because the open neighborhoods in a manifold are open neighborhoods in vector spaces. So anything that you did in calculus that was local and only used the fact that every point has a neighborhood which looks like an open subset of a vector space, you can do the same thing on a manifold. That's the idea. You could, in principle, make it, you could define an analog of a manifold where every point has an open neighborhood that's of some other model type. Right? We decided that we like open subsets of vector spaces because we can do calculus there. So we'd like to say that every point in a manifold has a neighborhood that looks like an open subset of a vector space. If there was some other kind of space that you liked, you could say that, oh, well, how about every point has an open neighborhood that's homeomorphic to, and then fill in the blank, but I don't know what you'd fill in the blank with. Because, I mean, manifold is a nice kind of space. It's sort of general, yeah, thing.
To show that it's homeomorphic, don't we also need to show that an open subset of GK sigma is also open?
Yeah, so that's going to be the next bullet point. So we have to say this is supposed to be, let's see now. So this is pi is a homeomorphism. So this thing was, this was just that U alpha is open in the affine space. We didn't say that it was a homeomorphism. Oh, sorry, this part. So let me erase this for now. Let me erase that, and it'll make you happy if I put it on the next line, probably. So we're going to declare. So I have to tell you what the topology is yet, what the topology is. And I think I mentioned it last time, but I didn't actually say it explicitly, or maybe I didn't write it explicitly. But I have to tell you what an open subset of the Grassmannian is. So I'm simply going to declare I'm going to declare a subset U inside of, okay, there's an L that shouldn't be there in the notes. Inside of the Grassmannian, GK F to the, it says GLK of F to the N, which is not what I meant clearly. To be open, if and only if U intersect G, K, sigma, these are the images, remember, of the charts, is open for all alpha in sigma in N, choose K. Yeah, so what I'm saying is that you declare a set to be open if and only if intersection with each of these things that are supposed to be open is open. Right? So what you're really saying is that suppose that you have a subspace given by a matrix. Right? Then an open neighborhood of this matrix inside of this vector space gives you an open neighborhood inside of the Grassmannian. Right? So if you want to know a small open neighborhood, just choose a chart and look to see whether the neighborhood is open there. Is that fair enough? Now, how do you know that's well defined? Right? If I took a subspace and I said, okay, that subspace is the row span of this K by N matrix. Right? Now, suppose, and this K by N matrix has an identity in these columns. Suppose that I'd chosen another K by N matrix that has an identity in perhaps some other collection of columns, and I want an open neighborhood there. Does the open set that I chose here, is it open in that other choice of chart? That's the question. Right, so if I take this, again, take this matrix, look at an open subset of this, look at open neighborhood of this matrix in the space of matrices of this form. So I'm allowed to wiggle the entries that aren't on that identity block. I'm allowed to wiggle those entries And if I wait, so that gives me an open subset inside of F k by n sigma. If I'd chosen Fk by n tau, yeah, so if this matrix has, so this matrix of course has rank k in the columns from sigma. But it might have rank k in some columns from some subset other than sigma. And I could choose to invert that submatrix and make that one the identity instead. Is the notion of open neighborhood the same in Fk by n tau as compared with Fk by n sigma? That's what this condition is really doing. It's saying that the notion of open is the same when you do it in tau and sigma. So let's do this in a little bit more detail. So this is now the last one. Let's set. So I need to know that this is well defined. The fact that this is well defined is actually a homework problem, which I think is on this week's homework. Is that true? It's not? It is? There's, let me actually see whether that's true.
Oh, wait, no.
Second one.
Yeah, number 15, prove that a subset of a manifold is open if and only if its pre-image under every chart is an open subset of a vector space. Right, so the point is that if you didn't already know what a topology was, I could define this to be the topology on the Grassmannian. Just say that it's open if and only if its intersection with one of these things is open. And the fact that that's well defined comes down to these things, these transition maps being continuous. That's what it's going to come down to. But let's do that explicitly here. So let's set F. I hope I have enough room to write this. F k by n sigma and then comma tau. That's going to be the matrices A in F k by n sigma. Remember, that means that A has an identity. This is F k by n sigma, right? That means that A has an identity block in the columns from sigma. But now I also want that A tau, which is, that's the columns of A indexed by tau, I want that to be invertible. Okay, so I'm saying, look at the k by n matrices that have an identity block in the columns from sigma, and in the columns from tau, they are invertible, which means that if I do things right, I can make it into a matrix with an identity block in columns from tau. Of course, when I do that, I ruin the fact that it has an identity block in the columns from sigma, but at least it has an invertible matrix in the columns from tau. Okay? So what is this? This is equal to pi sigma inverse of gk sigma intersect gk tau. Think about that for a second. What I'm saying is, let's look at the subspaces that I get by taking row spans of matrices with identity blocks in columns from sigma. Let's alternatively take the subspaces that come from row spans of matrices that have identity blocks, that have an identity block in columns from tau. If you can be expressed as a row span of a matrix with an identity block in sigma columns, and you can be expressed as a row span of a matrix with an identity block in the columns from tau, that means you're in the intersection of these things. And the condition there is exactly viewed from the point of Fk by n sigma, is that the columns from tau have to be invertible. If you have an invertible matrix in columns from tau, how do you express that subspace as the span of a matrix with an identity block in columns from tau? How do you do that? So again, if I had a matrix, if I had a subspace that's the row span of a matrix that has, now this has, actually it's not relevant that it has columns that are identity block in sigma. What's relevant is that if you have a subspace that's a row span of a matrix that has an invertible block in columns from tau, and I want the identity block in columns from tau, let's do this. So this, So if this has like this, if that's tau, just confusingly, 1, 2, 3, 4, 5, 6, 7. Ooh, 7 in both cases, very nice. Right? So if I know that my matrix is invertible there, how do I force it to be the identity there? Let's say this is A, and let's say that A tau is invertible. Then how do I make sure that how do I get now a matrix that has an identity block in those columns?
Multiply by A tau inverse.
Yeah, that's all. Yeah. Yeah, so the point is that A tau inverse A lies in F K by N tau. Very short statement afterward, right? It says that if you have a matrix that has an invertible square submatrix in the columns from tau, then if I multiply by the inverse of that invertible K by K matrix, well, then I have now a matrix that has an identity block in these columns. That's because matrix multiplication goes column by column in that way. Okay, so then pi tau inverse composed with pi sigma, that's going to map F, it's going to map Fk by N sigma tau. See, that tau tells me that I can multiply by the inverse of the matrix there, or inverse of the matrix that has the columns from tau. And it's going to map to Fk by N tau sigma. And the map is that it takes A to what? So remember, this is a matrix that has an identity block in the columns from sigma, but an invertible block in the columns from tau.
A tau inverse A.
Yeah, it's just this. It's just going to be A tau inverse times A. This now has an identity block in columns from sigma, but because A had an identity block in columns from sigma to begin with, then now the sigma block of this matrix is invertible. What is the sigma block of this matrix? Literally, what is it equal to? Yeah, it's just A tau inverse, right? Because if A had an identity block in columns from sigma, you multiplied it by A tau inverse, now that identity block became an A tau inverse. Simple enough. What can you tell me about this matrix A tau inverse? What are its entries? Its entries involve things like, cofactors divided by determinants and so on and so forth, right? Like it's got entries, it comes from the entries of A, and then maybe the determinant, it's got the determinant of this A tau in the denominator and so on. Those are rational functions of the entries of A, right? The entries here are rational functions of the entries of A. That actually completes the proof. But the point is that those rational functions, well, they're ratios of polynomials. They are also continuous. They are differentiable. They're analytic. And they're also ratios of polynomials. That's why we proved that it's a rational algebraic variety. Because in the end, if you wanted to prove that it was just a topological manifold, you wanted to prove that that the functions are continuous. Well, they're continuous because they're rational functions of the entries of A. So if you're going to prove that they're rational functions of the entries of A to begin with, you may as well conclude the strongest thing, which was that you actually have a rational algebraic variety. And then it implies that it's a topological manifold. Are there questions about this?
Would you mind walking? I understood each component of the proof, but would you mind walking through the general logic of why we took each step we did?
Yes. So do you want me to go starting from the beginning of the proof or just in the last bit?
Either would be fine.
Yeah, so say it again.
Could we do the beginning?
From the beginning. Okay, so the first thing to do is look back in your notes at the definition of manifold, which I'm going to do myself right now, because I have to know what I'm supposed to say. And there are a bunch of bullet points. There are 4 bullet points, right? The first thing is we needed to have maps. So we had the maps. Here they are. These are the charts, right? I told you what the atlas was in the statement of the theorem. So now I have to verify some things about these. I need to know the images covered. That is, I want my Grassmannian to be covered by the images of these charts. I'm supposed to be looking at a map, so an atlas for this space. And I need to, no matter where I am, I can get directions there. So I need to know that this space is the union of the images of these charts. That's the first thing that we check, right? The space is the union. We checked that in a proposition from last time. The next thing I want to check is that each of the charts is actually an open subset of a vector space. So why do we want to do that? Again, we want our manifold to be we want every point in our manifold to have a neighborhood that looks like a vector space. So I'm standing at a point in my manifold, and I want to know that locally around this point, it feels like I'm standing in a vector space. And that's what we did over here. Well, we said that each of our charts, it starts off from an affine space of the appropriate dimension. So the next thing we did was say, oh, well, wait a minute, but I'm supposed to know that I have an open neighborhood that looks like a vector space. So I need the notion of open to be consistent. And so then I told you what it means for a subset to be open. And I just defined it to be that you're open if in every map in every chart that you look at, you're open in that chart. And then the last thing we did was say, well, okay, what happens if 2 people are looking at different charts? Then is the notion of open from this chart the same as the notion of open from that chart? And then we checked what is the map, what is the function that goes, what's the transition function that goes from one of those charts to the other chart? And we checked that, oh, that transition function is given by a bunch of rational functions of the entries of A. And therefore, the space was a rational algebraic variety. Derek, did that answer your question?
Yes. Yeah.
Yeah, we were just literally going through just the bullet points in the definition of manifold. But then why did we have those bullet points in the definition of manifold? Because we want manifolds to satisfy certain things.
So is that declare a definition, actually?
This declare?
Yeah.
So the point is, up to this point, I didn't tell you what the topology on the Grassmannian was.
Yes.
So here I'm now finally telling you what the topology on the Grassmannian is.
So that's the definition of the open set.
Yes, that's right. That's right.
Grassmannian.
Yes, so I'm defining the open subsets of the Grassmannian to be exactly the ones whose intersection with any chart. Remember, there are only finitely many of these, so this is not so bad. But I want the intersection with the image of any chart to be open. That makes sense, right? If I've got a subset of any space, I can draw this over here. If I've got a subset of any space, here's my space, and I'm covering it by finitely many things like this. And I want to know, okay, I've got a point here, and I want to know, is this neighborhood, is that an open set? I just say, oh, well, is it open when I look at this chart? Okay, good. Is it open when I look at this one? Oh, good. Is it open when I look at this one? Oh, good. That's the point. So if you want to know whether something is open, it suffices to say that it's a union of finitely many open things. That's why we've actually used the fact that this is a finite set, although we actually don't need that. It's still true. If it's true for all charts, then it's still a well-defined notion, as you'll prove in the homework.
Can you elaborate on the definition for openness in any of those intersections?
In any of which intersections?
Like,
oh, in here?
No. Like the one above.
This?
No, like on the top.
Oh, here.
What does it mean for an intersection to be open?
Well, so what is this? So GK sigma is a subset of the Grassmannian,
yeah.
But you should think of it as the image of this thing. So what this is, what is GK sigma? It's subspaces that are row spans of matrices that look like this, with an identity block in these columns, right? And if the matrices that look like this, that's an affine subspace. And you know what it means to be an open subset of an affine subspace, right? It's a vector space, so I know what it means to be an open subset. I can look at the distance and look at everything that's less than or equal to and so on. Yeah?
What is the distance function in the affine space?
So if F is the real numbers, then I can take I can take any norm. And then the distance is the distance given by that norm. If F is not, if F is like, a finite field of 27 elements, then there's no notion of distance, there's no notion of a metric space or anything, but I can just declare these subsets to be open.
Okay.
That's the point. So this works even if the field isn't the real numbers. But the point is, we are assuming when I make this definition that I know what it means to be open inside of an affine space.
So just make some choice of being open in F, and then this follows from it.
That's right. Yeah. So you need to know what it means to be open inside of your field. So for finite fields, let me not get into it. Every subset will be open in some sense because they're finitely many points. But there are look up the word Zariski topology if you want to figure this out. So what that's essentially going to say is if you had, like, for instance, an algebraically closed field of characteristic P, then there is a notion of what it means to be an open subset, and essentially what it's going to be is the complement of any finite set is going to be open. If you have f to the n, then what you're going to say is that the zero set of a polynomial is closed. Which, by the way, makes complete sense. If you're in R to the n and you take a polynomial function, then the zero level set is closed. Why is that? Because if your function value is not zero, then there's a neighborhood around which it's also not zero. That means that the zero level set is closed. So what this says is if you have an arbitrary field, you can declare the closed sets to be the ones that are zeros of polynomials. I don't want to go into more detail about that. You should look that up. But the point is this connects to algebraic geometry. I wanted to give you this definition sort of independent of F because all that matters here is that the entries are rational functions of the entries of A. And that's well defined regardless of the field. It has nothing to do with the real numbers, the complex numbers, or distances, or metrics, or anything like that. It's that the functions are nice functions of the entries of A. And if the topology is the Zariski topology, then by definition, the open sets are the ones where polynomial functions are zero, they or don't vanish. Things like the determinant. I forgot who asked the question.
So, like when the theorem we want to verify is a manifold, so why do we need to consider the different charts, like
the different charts?
Why do we need to care about the defined open set? What's that part for?
Oh, so I made a declaration. I said that a subset is open if and only if its intersection with some chart is open. But what would happen, I said if and only if here, right? What would happen if you chose to verify it with sigma and I chose to verify it with tau? We could potentially come up with different answers where you say it's open and I say it's not. But that can't happen because the transition functions are continuous, that can't happen. That's why we have to check on different charts. And exercise 15 on the homework actually is the exercise that shows that we're making a consistent choice here. So what I was going to do next was just another example, but still linear algebra example. It's just going to be another example where instead of looking at single subspaces, we're going to look at chains of subspaces. Where was I? Here. Okay. Definition. A complete flag in V. So V is just a vector space. Is a chain. It's going to be 0. That's V0, contained in V1, contained in ... It's contained in V n minus 1, contained in Vn, which is V. So let's say this thing has dimension n. just so that we know what n means here, is a chain of subspaces. You'll actually only have to say this. I don't have to say that. You'll see in a second why I don't have to say that. Of subspaces. So V, and I want the dimension of VI is I for all I. In particular, the dimension of Vn is n, so V is a vector space of dimension n. So just chains of subspaces, that's all. So let's set FLN, stands for flag sub n, of F. That's going to be the set of complete flags in F to the n. Okay? We're looking at chains of subspaces. So the Grassmannian was, if you like, what happens when you look at chains of subspaces, where you just go 0 to VD to Vn. So they're very simple chains of subspaces, where you just, there's 0, there's the whole space in the middle is a subspace of dimension D. You're looking at all of the chains like that. That's the Grassmannian. Well, I'll say flag variety, flag manifold. So what we want to do is we want to, so the exercise is to express FLN as a quotient. Remember what we did with the Grassmannian? We sort of said that, well, every subspace of dimension D is represented by a K, K. Every subspace of dimension K is represented by a K by N matrix of rank K. But when you do that, you get subspaces lots of times, right? Because there's more than one K by N matrix that works. So we want to do the same thing for flags. So I'm going to ask the question, how do you write down a flag of subspaces? How do you write down a flag, chain of subspaces? So that's the question. So we want to express it as a quotient. The question is of what and by what, right? Of what and by what. And what that amounts to is, how do you write down a flag? And once you've written down a flag, what is the ambiguity that you had in your representation of what a flag is? So how do you write down a chain of subspaces like this? And I'm appealing to your, basic linear algebra. If I wanted you to write down a chain of subspaces, what's the first that you would do?
The sequence of matrices where each matrix is the matrix representation of the bases.
Sure, yeah, that's right. So what you're saying is, okay, well, it starts off with 0, no choice has been made there. Then I have V1. Well, what's V1? V1 is the span of something, right? So let's write something that it's the span of. Is that what you're saying, Jeffrey?
Yeah.
Yeah, okay, so V1, that's the span of some vector V1. So I'm going to use these, this thing means span of dot, because otherwise I'm going to have to write the word span a lot. I don't want to do that. Okay, this means is generated by. So V1 is generated by a vector called little v1. Okay, how about V2? What can you tell me about V2? This is a subspace containing V1.
So it has to contain everything. It has to be generated by V1 and by something else.
So it is generated by, it doesn't have to be generated by V1 and something else, right? It could be generated by V1 plus V2 and V1 minus V2. Neither of those is equal to V1, but it certainly can be generated by V1 and something else. What can you tell me about V2?
It would need to be linearly independent.
Right, so how do you write that? Say V2 is not in V1. Yeah? How about V3? Again, this is a subspace of dimension 3. It contains V2. So tell me how to generate it.
You could with V1, V2, and V3, such that V3 is more on the state of V1 or V2.
You could certainly start with V1 and V2, and then add in a V3 and you want that V3 does not lie in the span of V1 and V2. Dot, dot, dot. Right? So I can just start with a vector, and then add in another vector, then add in another vector, and keep doing that, just making sure each time that when I add in the new vector, it's not in the span of the previous ones. What does that mean about the matrix A? Which is, let's do columns this time, just for fun. What can you tell me about this matrix?
Full rank.
It's full rank. How do I write that? What's the cheapest way you can write that?
The stars.
Yeah, it's invertible. It's in GLN. It's in this group of invertible matrices, which, if you like, Nicole was saying, it's F to the n by n sub star. But then once we have n by n, let's call it GLN, general linear. Okay, so this is, why is that? It's because precisely that Vn is not in the span of the previous n minus 1. So what we've shown here is that the rank of the left k columns is k. That's this. Right? The rank of the left I columns is I. That's precisely what this is saying. Yeah, so the flag is just going to be, you give me an invertible, so the lesson from this is that if you give me an invertible matrix, I already have a flag. Invertible matrices, flags come from invertible matrices. If you give me an invertible matrix, then the column span of the left column has dimension 1, and the span of the left 2 columns has dimension 2, and the span of the left 3 columns has dimension 3, and so on and so forth. That's what it means to be invertible. So what started off sounding like kind of a complicated problem ended up with a really easy answer, right? Flags are given by invertible matrices. But, answer to Nicole's question saying that it has to be generated by V1 and V2, it doesn't have to be generated by V1 and V2, right? It only can be generated by V1 and V2. So what kinds of choices what kinds of alternative choices could we have made to get the same chain of subspaces? Now, if you give me an invertible matrix, then it does give you a chain of subspaces because the span of the left column, the span of the left 2 columns, the span of the left 3 columns, that's a chain of subspaces. But what additional choices, so what redundancy was there?
Change in basis, right?
There are going to be changes in basis, that's right. That's not important. On a snow day, I check. Okay, so then what kinds of changes in basis could we have, what kinds of changes in basis would have kept the chain of subspaces the same?
Upper triangular or lower triangular.
Oh, okay, that was a quick summary. So you're saying that upper triangular or lower triangular, in this notation, it's going to end up being upper triangular, as you'll see. So what's the slow motion way to say that?
Because Vn can be any linear combination of V1 and Vn.
Yeah, so Vn can be any linear combination of these things as long as the coefficient on, can be any linear combination of these as long as the coefficient on Vn was non-zero. Right, so Vn can be alpha 1 V1 plus alpha 2 V2 plus dot 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 plus alpha n Vn can be arbitrary as long is allowed as long as alpha n is non-zero. Right? Because if alpha n were 0, then Vn would lie in the span of the previous ones. Yeah, so that means that the change of basis that we're allowed is going to be allowed, we're allowed to take any column over here that we want, right? So this is going to be star, 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 and then this one is not 0. Fair enough? So I'll write it this way. Maybe I'll write it this way. I'll write it as F, 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 and then F star. Fair enough? We can take our coefficients to be arbitrary, but the bottom one has to be non-zero. What do you know about the previous one? What about Vn minus 1? And all we need, so this is allowed as long as alpha n minus 1 is not 0. What does that look like over here? That looks like we've got our f star sitting here, and then f like this. And then dot, 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 we get that v2, let's do it v3. v3 is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. So what does this say? This says alpha 3 is not 0. So dot, dot, dot. This is f star, f, and then we have f star, f. And then the last one is f star. Let's just be sure that that makes sense. What is this f star telling us? That upper left-hand one, in terms of the board over here.
Just something times v1 that's not 0.
Yeah, I need to span this line. How do I span a line? I choose a basis vector for the line. That basis vector can be any scalar multiple of v1 as long as it's not the 0 scalar multiple. That's what this one is saying. Yeah, okay? So let me make a definition here. So let's say that Vn plus, that's going to be, well, what's this? And this is called a Borel subgroup. So this is contained in GLN, and that's the Borel that's a Borel subgroup. It's the Borel subgroup of upper triangular matrices. There's also a lower Borel subgroup, which would be Bn minus. But it turns out that there are other subgroups of these things. All the conjugates of these things are called Borel subgroups. What does that mean? It means that if I change basis in an arbitrary way, and look what it does to this, it takes it to another subgroup. It won't look upper triangular anymore, but the point is in some basis it's upper triangular. So a subgroup is Borel if in some basis it is upper triangular. Lower triangular matrices, by the way, are upper triangular in the choice of basis where you reverse the basis. Then they're upper triangular. Okay, so what's the proposition now? So we've said how to express every flag. We've said how to get a flag. A flag is obtained from an invertible matrix. And we've said that the redundancy is that if you change the invertible matrix by multiplying, by the way, on which side? On the right by this matrix, then you end up with the same flag. And so the proposition is that the space of flags is GLN modulo Bn plus like this. So what that says is that G, like A goes to our flag B dot, right? And then AB goes to B dot. If and only a B lies in Bn. And we've already proved that actually. So the proof is, is way over there. It's all the way on that side. We actually just proved it. All right, we said that every matrix gives us a flag. How do you get the same flag? Well, if and only if you change basis in this way. Now, as I say change basis, it's not a change of basis thing. It's if and only if you chose your basis differently. That's different from change of basis. We're actually replacing the choice of V1 with the choice of alpha 1 V1. Actually, it's replacing with the choice of what we're now calling B11 times V1. We've already done the proof. That's the whole point. We've actually just proved this proposition, right? So now we've expressed it as a quotient. So now here's the question. Is FLN a manifold? Is it a rational algebraic variety? And so on and so forth. Most of this exercise will be done by you in the homework, but let's talk a little bit about getting to that point. Let's produce a single chart, and then you'll produce the other charts. variety? The answer is going to be yes. So what do we want to do? How did we prove that the Grassmannian was a manifold? What did we do to do that? Well, we have these open subsets, right? And we said that each of these open subsets sort of covers most of the Grassmannian, but not all of it. So how did you cover most of the Grassmannian in a single shot from an open subset of an affine space, or from an affine space itself? What we said was, well, you know, if the left k columns are invertible, then I can make the left k columns into the identity, and now I represent my subspaces uniquely. Right? What I said is again was that we want to find some big open set that's represented sort of exactly once in a nice way. We want to find a big open set. Yeah? We want to find a big open set that is a subset of a vector space. Big open subset that is open in an affine space. That's the first thing we want to do. And then we're going to want to find lots of copies of that. So let's first do this. Then we're going to want to find enough copies to cover. Yeah, so how do you find a subset that's going to be an open subset of an affine space that's going to give you flags uniquely? Well, what would you like to say in some sense? So, in general, if you give me a matrix, let's assume, and here you'll see what's going to happen. Assume that A is, and I'll put it close, generic. We don't know what generic means yet. We'll know what it means when we're done. The point is that when we make A generic, you'll see that you're allowed to do, anytime you want to do an operation that cancels something or divides by something, and you can assume that the thing is non-zero. That will be contributing to what generic means. It means that the entries are random, and if you want them to satisfy any condition, as long as that condition is open, you're good. So the condition of being not equal to zero, that's an open condition. Right? To be equal to zero, that's a closed condition. To be not equal to zero, that's an open condition. So for instance, let's use B11, right? This is the entry over here, that's B11, right? We're allowed to scale. Let's use B11 to make the entry A11 equal to 1. Remember, we've been given a matrix over here, capital A, and now I want to do things to it and find a standard form. What did we do in the Grassmannian case? We said, oh, let's look at the reduced echelon form. And if you choose a generic matrix, K by N, and you take its reduced echelon form, what is that reduced echelon form? What does it look? Where are the pivots?
First left K.
In the first K columns, right? So if you choose a generic K by N matrix, its reduced echelon form has the pivots in the left-hand K columns. So we're going to do something similar here. We're going to assume that our matrix is generic and then reduce it in the appropriate way. And we'll, when I say in the appropriate way, we're going to reduce it upper triangularly. This is going to do column reduction for us, but it's going to do column reduction where you're not allowed to swap any columns. That's essentially what we're doing. We're going to column reduce without swapping columns. When you do column reduction or row reduction, what prompts you to swap a column? Or to swap a row in row reduction? What's the condition that said, oh, we have to swap something? What happened when you did that?
A pivot went below the diagonal.
Yes, but what caused you to, it was below the diagonal, so then, yeah, so when you have a pivot that's below the diagonal, what's between the diagonal and the pivot?
0.
Zeros. There are zeros. If you chose a generic matrix to start off with, those zeros won't be there, right? For an entry to be 0, that's a special thing to happen. So if you started off with a generic matrix, those zeros won't be there, and you'll be able to row reduce or column reduce without swapping any columns. That's what this is doing. So let's just see what that condition actually looks like just in the first couple of steps. So we're going to use B11 to make A11 equal to 1. So what's happening is that we're going to choose our, I guess I'll leave this picture up so that you can see what B looks like. But so now we're going to have B1. We're going to change bases like this. So we're going to take A11 inverse, right? Multiplication by this. If we put zeros down here, like this, the multiplication by whatever matrix this is going to end up being is going to rescale the, whoops, I should have left the A here. It's going to rescale the upper left-hand entry, so A. It's going to be A11 up through A1N and down through AN1 up through ANN, like this. So when I multiply this matrix by that one, it's going to rescale to make A11 equal to 1. Yeah? Now I have no control about what it does to the lower entries here. But I can, if I want to, I can use the other entries here, right, to cancel off the other entries up in that top row. So I'm going to use the entries over here to cancel off the entries in the top row. So I'm going to use now B12 up through B1N. I'm going to use those to cancel. A12 up through A1N. How do I do that? What I do is I put negative A12 on A11 inverse, and then I put a 1 there. Fair enough? And so I take this linear combination, it's going to say the second column is what you get by taking this column, multiplying it by A11 inverse, and a minus sign. Now you multiply it by A12, that's going to make this negative A12 up there, and then you're going to add it to that one. It's going to be 0. Yeah? Negative A1N, A11 inverse. So if I take this to be my B, then I've successfully made it so that AB1 is going to be now 1, and then stuff, and then zeros, like this. Like this. Continue in this way. Right? So we want now AB2. That's going to be 1, and then a bunch of zeros. And then it's going to be star, and I don't know what goes there, and then 1. And then a bunch of zeros. And beneath that, it's going to be stars, like this. Okay? And you keep going like this.
Is B2 a product of some matrix with B1?
Oh, I'm sorry, this should be AB1, B2. Sorry, we want to do B2 to this matrix. Yeah, thank you. So we're going to use now B22 to make A22, the new A22 equal to 1. And then, so the point is that this, and then this, and then this, and then this, and then we want B23 up through B2N to cancel the new A32, whoops. No, should say A23 up through A2. believe that's incorrect, but I'll check to make sure that that's right. Just check those. And dot, dot, dot. What's the conclusion that you end up with this?
Yeah, are those B's? They're B's of different matrices, right? Because
Yes,
the
they
first
are.
two B, yeah.
Yes, they are. So it's actually say really new B22 and the new there. So this is B1. This is in B2. Yeah?
Yeah, thank you.
So the point is that then A, B1 up through Bn is going to be, what's it going to look like? It's going to be zeros up there, ones down the diagonal, and then stuff underneath the diagonal like that. So this is going to be called UN minus, which is called the unipotent subgroup. Which is just the lower Borel group, which put ones on the diagonal instead of arbitrary non-zero elements. Okay? These are just names given to these things, right? They have more general meanings in sort of representation theory and stuff, but here it's just a name that I can use. So think of uni means one, so it's a unipotent there. If I put zeros there, what would I call it? It'd be nilpotent instead of unipotent. It wouldn't be a subgroup, it'd be the nilpotent matrices, but nilpotent, so if you put zeros there, then some power of the matrix gives you zero. That is, the characteristic polynomial is just, is zero. Sorry, it's t to the n. Right. Okay, so then the proposition just says that UN minus injects into FLN, which we remembered we expressed as GLN modulo Bn plus. So the point is that matrices that look like this determine a subspace uniquely. That is, if you have a subspace, it's not a subspace, a flag. If you have a flag that is the span of the left column of this, the span of the right column of this, the span of the left column, the span of the left two columns, the span of the left three columns, and so on, then if there's a matrix for which it is this matrix that looks like this, that gives you your chain, that gives you your flag, then there's a unique matrix like this that gives you your flag. That's the point. That's the content of this. And the proof is homework. Not this homework. It'll be homework after the midterm. Yeah, I'm not going to ask you to prove this on the midterm. It's not bad. It's just linear algebra. In the end, all we're doing at this point is just 221. So that's the first statement, is that that's an open subset. Okay, now, what was special about this column reduction? What was special about this statement when read in 221 says that a matrix that looks like this, a matrix whose column reduction looks like this, doesn't use any permutations of the columns. That's what this statement comes down to. It comes down to a matrix whose column reduction looks like this, doesn't use, a matrix that looks like this, its column reduction doesn't, a matrix whose column reduction looks like this, doesn't use any permutations. So if we didn't use any permutations for this chart, what we should do is say, all right, allow me a fixed permutation to make it look like this. So if you just allow me to permute the columns, so there must be some permutation of the columns that makes it so that the column reduction doesn't use any permutations anymore. Just put all the columns in the correct places to begin with. And that's what the next statement is going to say. So the theorem is that FLN is a rational algebraic variety with atlas, and it's now going to be W, let's write it this way, W times UN minus goes to GLN log V plus, EN plus, such that W is a permutation matrix. Permutation matrix means it has 1, 1 in each row and column. The proof is, again, that's simply the whole. But I won't ask you to do this for the exam.